Thank you. So over the past few years, advancements in instrument resolution, satellite stability, and lower sensor operating temperatures require a better understanding of the impacts of jitter on high performance imaging beams. And so, there we go. So what is jitter? Jitter is the micro vibration of satellite platforms that can cause periodic instability in the satellite's attitude. And it's caused by moving or vibrating components, and is really a fundamental limitation for all satellites as it affects their precision pointing and accuracy. In this figure from the European Center for Space Sciences, we see the impacts of jitter on a typical imaging system. On the slides on the left shows a blurred image that has not been corrected for jitter, and as you move right, they apply varying levels of jitter correction to finally obtain an unblurred image. Another way of visualizing jitter is in this plot here, where you can actually see the centroid jitter on the focal plane moving around in blue against the requirement in red. And this is one way of characterizing jitter, and I'll come back to this in a little bit. And so jitter disproportionately affects smaller satellites. And the idea is from this plot here, adopted from Pong in 2018, where we plot launch mass in kilograms against the pointing performance of the satellite measured in RMS arcseconds. And you can see that for very large satellites and very kind of flagship missions like Kepler, JWEST, HST, and TESS, in that kind of 10 to the 3, 10 to the 4 kilogram range, we see very exquisite pointing performance from kind of semi-arcseconds to milli-arcsecond. And as you move left or decrease the mass, to 10 to the 0, 10 to the 1, to more of this small satellite and CubeSat regime, you see a more modest pointing performance. And the exception is Asteria, and I'll talk about that a little bit later. And so the reason for this is due to the fact that in these smaller satellites, the attitude control system takes up a significantly larger fraction of mass, or as a proportion, it's a lot larger compared to larger satellites. And in this plot from Douglas et al., we see that as spacecraft mass increases, the ACS mass fraction decreases exponentially. And so for something like a 6U CubeSat that weighs about 10 kilograms, we expect the attitude control system, which is the reaction wheels, magnetorquers, if they're gyros, to take up something like 20% of the satellite's total mass. And knowing this is important because we're now entering a time where these small CubeSat and small sat missions are becoming more and more capable. Taking a look back at one of the first small sat missions, the variability and oscillations of stars, or the MOST mission, was a mission to obtain long-term optical photometry of some of the brightest stars in the sky. And this satellite had a size of 60 centimeters by 60 centimeters by 40 centimeters and a mass of about 50 kilograms, making it equivalent to about a 24 or 27U. And it achieved 10 arcseconds RMS of pointing, which was actually very good for the time and sufficient for pointing requirements. With a 15-inch centimeter telescope as its payload, this is very much nowhere near the diffraction limit. And so, for these mission requirements, it was okay. It was a great performer and really paved the way for these precision pointing satellites. Next, as a complement to the MOST mission, came the Bright Target Explorer. And this mission was, again, an optical photometry mission to survey very bright stars working in a 5 CubeSat constellation. And each of these CubeSats was an 8U, and each of them individually achieved a 51 arcsecond RMS pointing performance with a very small 3 centimeter telescope aperture. So again, nowhere near the diffraction limit. Kitsune, on the other hand, is a more recent Earth observing remote sensing mission. This was a 6U imaging CubeSat for basically wildfire imaging. And it achieved a spectacular sub-5 meter ground sampling resolution, which is very much near the diffraction limit for the optics of that satellite. And finally, we have Asteria, which is probably the highest performing CubeSat to date, and it achieved a remarkable half an arcsecond RMS pointing performance for optical photometry. And this is when this was achieved with a second stage focal plane array correction. It basically worked the same way that in-body image stabilization in modern digital cameras work, by basically shifting the focal plane to compensate for jitter caused by the system. And this, given its optics, was actually a diffraction limited system, right? Your diffraction limit, at least at the highest end, was almost 2.3 arc seconds, and it achieved a 0.5 RMS pointing stability. And so now jitter is something that mission designers must be acutely aware of when they design missions. Now that we are capable of, CubeSats and small sats that are capable of diffraction limit or near diffraction limit pointing. And so in this plot from Dehaney and Salazar, it shows kind of regimes of designs and ideas for managing jitter at different levels. And so for missions with greater than 10 arc seconds of pointing performance, we say that it is enough to kind of characterize and understand the sources of jitter that we have. And so certainly missions like MOST or BRIGHT fit into this category. For missions, as we move down to kind of case 3 and 4, we have missions like Kitsune and Asteria that I talked about before, where the minimization of jitter drives the system design and the requirements for the mission. Take Asteria, for instance. I kind of wanted to highlight maybe one way to interpret this chart. Take Asteria, for instance, the mission that achieved half an arc second pointing stability. If you look at instrument control here, the difference between moving from case 2 to case 3 is the addition of compensation. And so I would say the combination of both functional design and compensation design. Functional design in this case was because this was an optical imager and thus didn't need any active cooling in the way that infrared detectors might. So in that sense, because cooling was achieved passively, we're not introducing any sources of jitter. And then the compensation comes in with that second stage focal plane array correction. So just, I guess, an example of how to interpret this chart here. And so as you move down to cases 5 and 6, those really represent state-of-the-art and beyond state-of-the-art designs. And this is where, missions like James Webb and Hubble kind of fit in. But it's important to realize that jitter, I guess, takes up characteristically different areas in the quote-unquote frequency range of the satellite. And below 1 hertz, we get effects from multi-body dynamics. These could be gravity gradient torques, solar radiation pressure, or the very minimal atmospheric drag that might occur in low Earth orbit. And as we move between 1 hertz and about 1 kilohertz, that's where we really begin to see the jitter from active vibration sources like cryocoolers and reaction wheels, gyros, and other moving parts of the satellite. And so the first fundamental harmonics may exist between 10 to the 1 and 10 to the 2 hertz, and then everything beyond that might be higher order harmonics. Okay. So now that we understand what jitter is, let's talk about some ways that we can characterize it. And I'll organize these into 2 kind of broad categories, what I'll call on-ground methods and then in-situ methods. So for on-ground methods, we use Kistler testbeds or piezoelectric dynamometers and finite element analysis. So let's talk about Kistler testbeds first. Kistler testbeds, or more generally piezoelectric dynamometers, use the piezoelectric effect to measure jitter. This is an effect when single crystals can release charge that is proportional to the mechanical load applied to them. Quartz in particular is a very good choice for this because they have a high stiffness and don't experience a sensitivity loss over time. And this is used in applications such as very expensive and specialized test setups, like the one picture here, where you have a piezoelectric dynamometer on top of basically a vibrationally isolated table or bench. And then you have your test article, your test subject attached, or not attached, but mounted on top. And then you would proceed to conduct your jitter testing there. This is an example of one such application where you see a cryocooler is actually on top of a dynamometer. That's that Kistler 9139AA. And then you can actually see more piezoelectric sensors, the 8763B and the 9347C there. And, just by looking at that picture, right, you can kind of see that, for a very small and compact cryocooler, we have to have this, it looks like a whole other masses of instruments and devices hooked up to it just to obtain jitter. And you can imagine that affects the way that cryocooler exports vibrations. And indeed, that is the case. But nonetheless, we use these because of their exceptionally high span to resolution ratio. And they can often measure jitter in 6 degrees of freedom, like shown in that picture. So your 3 translational axes and your 3 rotational axes from Marquette et al. And you can model dynamometers as a lightly damped second order system. And this is important because when we talk about the limitations of these dynamometers, we see that basically we want these dynamometers to be able to measure higher frequencies as well as support larger systems. But this is fundamentally limited by their design. And so if we take that lightly damped second order system that we saw before, we model it here. On the left is just the dynamometer. We see the adapter plate on top. K could be your spring stiffness, and M is just the mass. And so if you take, remember from your physics 1 class, the natural frequency of such a system, this is just 1/2 pi times the root of the spring constant divided by mass. So the important takeaway from this equation is that the natural frequency is inversely proportional to the mass, or the root of the mass. And this is important because when we add a payload or a test article on top of that, we are increasing the mass that goes on top of that dynamometer. And you can imagine that this reduces the natural frequency of your system. And that's important because you don't want the resonance effects of your system to affect the way that you take measurements, right? They'll basically amplify vibrations that occur at that frequency, which is what you don't want, because you want to measure the vibrations that are coming from that test subject specifically. And so you see that the working area then is about 1/3 of the natural frequency. And so this is a problem because not only are you limited with how much mass you can actually put on these dynamometers, but also the size, right? You can imagine that if you had a larger plate, say you wanted to test on a 6U or an 8U, right? That larger plate has more mass and will bring down the natural frequency of the system anyway. And you could say that, well, what if you changed what that plate was made of? Like, what if you used a less dense material? And that's been done. They went from steel plates to using ceramic plates, but your natural frequency only is up to 2000 hertz, and you can only maintain dimensions of about 400 millimeters. So still not enough to test on something like a 6U, and your natural frequency is still at about your working area, right? If you go 1/3 of the natural frequency is still on the order of about 700 hertz, which is not even a kilohertz. So with those limitations aside, though, you can obtain very detailed disturbance models from your piezoelectric test bed, assuming that you can test in that working area. And so what we do with this is we obtain very detailed models of disturbances brought on by components in component level testing. And then once we know the exported vibrations and the profile of those components, we use finite element model to obtain a transfer function for the system. And this transfer function is usually from that location of the disturbance to another location of interest, which is generally the focal plane or the optical axis. And then we'll use frequency response analysis to basically obtain the line of sight motion, resulting in a power spectral density plot, like this one shown here from Carpenter et al., where you basically see the line of sight motion in the frequency domain or as a function of frequency. So here's a flow chart of the typical jitter analysis process using disturbance data and a system transfer function. We start up here in the upper left with the disturbance data from a piezoelectric dynamometer, for instance, and we obtain both the force and the moment measurements, which we move into the frequency domain, take the Fourier transform of it, generate a power spectral density plot, and at the same time, that structure resonance in the frequency domain, that's your system transfer function. So what you're going to do is you'll basically multiply the PSD and the transfer function together, and then sum them up to obtain both the force and the moment information to form a full combined line of sight motion profile. So finite element analysis sounds great and all, but there are a few issues. And one of it is that it's generally known that the prediction accuracy of finite element models tends to decrease as the frequency of interest increases. And this tends to affect the amplitudes that you measure more so than the actual frequencies, the identified frequencies themselves. The reason for this is it relies heavily on the assumptions that you make about the subassembly and component interfaces. You can imagine that it's impossible to capture, the force that a screw might be holding two plates together in a finite element model, and that will affect how vibrations are transferred from one component to another, and basically affecting the boundary conditions of that analysis. And so high fidelity, the other issue is that high fidelity FEMs might not be available early enough between your PDR and your CDR. And then remember that high fidelity FEMs, if we recall back to that plot that showed the cases of mitigating and managing jitter, start to be required for managing cases 3 and above, which was on the order of 0.1 arc seconds RMS. And so this was an example, or an example of this was the reaction wheel imbalance that was found for the Chandra Space Telescope. They discovered that the reaction wheel imbalance was causing a vibratory mode in the satellite at their CDR, causing them to basically, at that stage, have to devote time and resources to addressing that issue. And so this is what a typical jitter testing campaign might look like, right? We start with component level disturbance characterization. Then we move into satellite bus level testing and AD and ACS testing. All the while, we are testing the transfer function that we obtained from finite element modeling. And in parallel to that, also looking at what our payload is doing and how our requirements are affecting the jitter of the payload. Then all those come together in the observatory level testing where everything is fully integrated. And then that testing is done. And then once it's in flight, we also want to characterize our jitter in flight to validate our models. And once we have that data, update the models and the structural transfer function testing to see if that is accurate. And speaking of in-flight observations, we're going to talk about some ways that jitter can be measured in situ. And I classify them into 2, I guess, ways, which is to sense jitter directly through attitude measurements or through using indirect sensing. All right, so direct sensing. Direct sensing is, as it sounds, you're just using high performance attitude measuring sensors to record jitter. This was done in Landsat 7. It had the angular displacement assembly that reported jitter, reported the, angular motion of the satellite at a rate of 2 milliseconds. And this is also done in the Yaogan 26 satellite, featuring, and it's using its suite of attitude sensors like a star tracker, gyro components, and an angular displacement sensor, was able to fully characterize jitter between 0.2 and 450 hertz. And so direct sensing is nice, but some missions will not have the budget, whether it's monetary, mass, or power, to support these high performance sensors on them. So another way that people can measure jitter is through indirect sensing. One of the first ways to do this is to evaluate a point spread function, or the way that PSF is affected by jitter. And this was done to evaluate the Hubble Space Telescope's problematic jitter in late 2017 by Anderson and Sabi. And what they basically did was they compared the spatial and temporal variability of a PSF from the nominal jitter case, which is pictured on the left, to the problematic jitter, which is pictured on the right. What they basically did was they simulated this point spread function and then added in elements of jitter to affect it and see what that PSF would look like afterward. And they found that the jitter adds about 11 milliarc seconds of RMS pointing error, which was not ultimately enough to affect any of the precise science that the Hubble Space Telescope's Wide Field Camera 3 was doing. Another method to use, and is actually, one that I thought was really cool, is to use optical correlation. And this is based on the Joint Transform Optical Correlator from this paper by Yutamulia in 1992. It's a really fascinating paper. Basically, what this method does is it computes the power spectrum by directly interfering the image that you're taking with a coherent light source. And what you'll get out of that is basically you'll get an image of the spectrum in the middle there. And so that's important because normally to obtain that spectrum, you'd have to actually go ahead and compute the Fourier transform of that image, and then you'd have to go ahead and square the magnitude of that Fourier transform to obtain the power to obtain that power spectrum. But this actually just images or puts that power spectrum directly on the CCD from the interference. And that's nice because you can correlate two successive spectra to obtain a correlation image down at the bottom, and the separation between the two peaks correlates to the movement of elements in that image. The nice thing about this is that it has a high signal redundancy based on this fact, and it's very has little dependence on the actual image content itself. But I will caveat that to say that this is a Fourier-based method, so probably won't work as well on smooth or smooth images or images that might contain features that could confuse a Fourier transform. This method was really fast, performing up to 10,000 correlations per second on a fairly small 128 pixel image, and had a detection accuracy of 0.1 pixels RMS. Finally, one of the last methods I want to talk about is parallax imaging. In parallax imaging, we use the fact that some imaging systems will have several CCDs, which will have overlapping regions as shown there, or overlapping regions, imaging regions, or footprints, as it's called there. These overlapping parts will image the same ground target at slightly different times. And while it's imaging these ground targets at slightly different times, the important piece of information is that it's simultaneously affected by the same jitter. And so from this picture, right, you see the images and the offset, and you can establish a relationship between the jitter and the target's offset between the two different images. But the problem with this method is obviously that it necessitates you having multiple CCDs in your imaging system, which is not generally true for small-sat missions or missions in general. So as a recap about in situ methods, we can characterize jitter and conduct analysis without the use of a finite element model, which is nice because we'll get a very accurate representation of the jitter. And we're also in space. We're not affected by dampening from air or any gravity effects, and we're also in microgravity. So gravity is less of a force. The problem with in situ methods, though, is that you can only obtain this information after your satellite is launched. So you cannot use any of these methods to characterize your system on the ground or to see if it meets requirements before delivery or as part of a design and validation process. And so some people have leveraged the fact that you can actually use finite element model free methods of measuring jitter. And this is what I'll talk about in the related work section. The first is from Taniwaki and Okami in 2003, where they used a laser to measure the translational displacement of a flywheel on top of a floating table or an air table using a CCD and laser sensor. So the flywheel is mounted there, and then the laser sensor just measures the displacement caused by the operation of the flywheel. The theoretical resolution for this sensor was 0.1 microns, which is very good, very accurate. And they found that it actually achieved higher sensitivity for lower frequency disturbances than with traditional piezoelectric sensors. Moving to maybe more recent times, Ishola et al. Performed two experiments to explore platform jitter on a 6U platform shown here, as well as a hexacopter drone shown there. And so in their experiment with the 6U system, what they did was they used piezo sensors to basically measure the ADCS exported jitter and correlated that movement with the optical displacement that they saw by using a laser. So they had a laser transmitter inside of the CubeSat structure that would be incident on a quadrant sensor, and they would basically correlate the displacement of that laser with the measurements from their 3-axis sensor. They also, in their drone experiment, they put an accelerometer and a gyroscope in the drone module and recorded vibrations while a optical receiver monitored the movement, principally in the same way as the CubeSat experiment. They found that the 6U CubeSat jitter was found to be about 1 milliradian, which in arc seconds comes out to about 260. And the drone jitter showed a lot more, about 90 milliradians in in pointing jitter, which is about 18,000 arcseconds. Finally, in Lee et al., it's a lot, yeah. Finally, in Lee et al. In 2023, they attached an imaging system or a camera to their reaction wheel assembly, shown here. And what they did was they imaged a PSF and used the motion of that PSF to monitor jitter. The optical vibration isolation platform and the integrations here was all used to just generate a nice clean PSF. That SPMI is the camera, and the ADCS system is with the 3 directional flywheels are shown there. And so the interesting thing about this piece of work was that they investigated the effects of various wheel speed combinations and configurations, I guess you could call them. In this table, what they did was they first started out by running each wheel individually and looking at the typical motion peaks and x-axis, right? So you'd see one at pixel motion at 470 hertz might be the way to interpret that. So they've collected the individual measurements at fixed wheel speeds. And then in table 2, they generated a number of combinations running different wheels at different speeds. And the idea was to see if the results in table 1 would basically form linear combinations, right? Proportional to what the results in table 2 might suggest. So, for example, in speed combination number 1, the X flywheel was spinning at 2,700 revolutions per minute. The Y flywheel was going at 3,000, and so was the Z flywheel. And the idea was that is the result of combination 1 the sum of X flywheel running individually at 2,700 hertz, the Y flywheel running at 3,000 hertz, and the Z flywheel running at 3,000. So what they found was that it's not, right? The operation of running multiple flywheels at different speed combinations will result in the excitation of modes that aren't present in running the 3 individually. Right. So finally, moving on to what I pretty much did for my master's thesis, was to develop an optical metrology system to actually leverage a finite free measurement of CubeSat jitter and then test it on a fully integrated system. And so for the components of the system, we wanted a few things. We wanted it to be inexpensive. We wanted to have commercial off-the-shelf availability. And we want to be able to scale the system to measure jitter in multiple degrees of freedom, as well as minimally modify the moment of inertia. So a quick overview about the operating principle of this metrology system is we used a stationary optical laser, a small mirror, and a position sensor to record very tiny deflections caused by satellite vibrations. So start with the optical laser. Fiber optic cable feeds a collimator. We have the mirror mounted to our satellite, which sits on top of an air bearing. We turn on the laser, right? Shine it against the mirror. Vibrations in the satellite cause deflections of that laser beam onto the lateral effect position sensor. And out of that position sensor, we get voltages, which we can then convert into digital position values. And so I'll be covering a few of the most important components here. I won't be covering everything in the interest of time. But the first component that I want to talk about is what we used for our laser source. We used a Thorlabs 635 nanometer benchtop laser source. This one was nice because it offers high stability over operating timescales, and has commercial availability. You can pick it up, order it right now if you want to. Another really nice thing is that it has visible operating wavelengths so that we can actually see the alignment of the system as we're testing it. The mirror that we used was a Thorlabs tiny 1-inch diameter mirror that's mounted on top of a kinematic mirror mount. It's a very lightweight mirror, so we don't expect it to modify the moment of inertia really significantly. And the mirror mount allows for tip tilt adjustment to help align the system better. The last thing, and I think one of the most important components, is the use of a lateral effect position sensor. Would be the Thorlabs PDP-90A. This one, very high accuracy. The nice thing about using a lateral effect position sensor instead of maybe like a CCP or a pixelated detector is that it's independent. The measurements are independent of beam shape, size, or power. And so you can obtain very accurate position measurements without going through optical wavefront correction or worrying about gain or anything like that. This particular sensor reports the power center of the incident beam. So you can imagine a circle, it'll just find the power center of the beam and say that that's the centroid. The 635 nanometer line filter is attached. That's that tube structure you see sticking out of it. And that's nice because we want to reject any broadband light or light that is not coming from the laser. This K-cube that we used is a position sensing detector and auto aligner. It's actually a high-end compact controller that is used for these applications. We chose it because it had very nice and simple interfacing with the lateral effect position sensor, and we could obtain beam position measurements in its monitoring mode and offered 16 bits of resolution. For our analog to digital converter, we chose the LabJack T7 Pro that's pictured here with that K-cube attached to it. It's a very high resolution 24-bit sigma delta analog to digital converter that offers a effective resolution of 17.5 bits because of the rate at which we were sampling. It's basically a trade-off between your sample rate and your accuracy. This one's nice because it features USB interfacing, and we are able to basically write some code to have it pull data in Python. So this is a table of all the components and cost for the metrology system, looking at something a little less than $6,700, which is actually really nice because when I checked on Kistler, the vendor for a lot of those piezoelectric sensors and test beds that I mentioned earlier, this morning, if you wanted to order parts to make a jitter measurement setup, you have to request a quote from them. And they won't tell you the availability of their materials. So this is nice because you have the costs here and it's all readily available. And you basically, if you wanted to implement such a system, you would know exactly how much everything will cost up front and what spec you will have for each of these components. So now I'm going to talk a little bit about how we use the system and to actually get data. So the idea is that we're going to use Fourier analysis to analyze jitter in the frequency domain. So going back to the plot here, I'm really going to kind of focus in on that section right there in the triangle. And so when we set up the metrology system, right, that laser collimator, that triangle is now here. That laser collimator puts the beam incident on the mirror. The mirror reflects it back to the lateral effect position sensor. The distance between the mirror and the lateral effect position sensor, I'm going to call L, or that's the throw distance of that laser beam. That value is basically the distance over where the deflection happened. And so if you know that distance, you can obtain an angular displacement because you can measure the displacement on the position sensor detector. The way that the position sensor detector is set up is that it records the X value of the centroid in this direction. We're parallel to the ground in the way that I have it set up, and in the Y direction, which is perpendicular to the ground in the way that I have it set up. And that's actually real data in that little GIF there of the reported centroid moving on the detector. So that's like what your actual raw data might look like. So it's reporting the centroid of that moving beam. And it's kind of cool because you can actually even start to see a little bit of periodic structure in the movement by itself. All right, so the first thing that we're going to do is we're going to use those components to collect time series. Just basically measurements of position versus time. The X data I'm going to color in blue, and the Y data I'm going to color in orange. So we have one for the X-axis and one for the Y-axis, two time series of data. The next thing we're going to do is to mean center the data, so we get basically displacement values from the mean, and then divide by that throw distance L. This gives us the angular displacement values that we want. So same plots, just now mean centered and in angular displacement in units of arc seconds. The next thing that we're going to do is we're going to take the Fourier transform of those time series, and then from those Fourier transforms, obtain the power spectral density from them. And the reason why we want to use a power spectral density plot is because this gives the portion of power that's contributed by each frequency component of the signal. And these are what the power spectral density plots look like. You can see now on the x-axis you have units, you're in units of frequency instead of time. And then on the right, you have basically a spectral density in arc-seconds squared per hertz. So after this, we're going to use the fact that the variance of a zero mean random signal can be found by integrating those power spectral density plots between a minimum and a maximum frequency. It's given by that integral there. Basically, in this plot, it's just the two PSDs plotted over each other, and you're just integrating from a frequency that you are interested in all the way to as far right as possible. So once you integrate both of those plots, you'll have a variance value in the x direction and a variance value in the y direction. The total variance will just be given by the sum of those two values. And the n sigma value is given by n times the square root of that variance. RMS, or when I refer to the RMS pointing, that's just the case for n equals 1. Right. So now that we have a ways to quantify the jitter value, the next thing that we want to do is we want to use the system to investigate system dynamics. And that will be done by attributing modal frequencies to vibrating sources. And we'll do that by creating permutations that will incrementally add or alter sources. So, like I said, we want to attribute modal frequencies to vibrating sources, and we'll be doing that by incrementally adding or altering vibrating sources, and then we'll analyze those results also in the frequency domain. So here I have a table of what that might look like. I'll come back to the details of this table, but the important takeaway is that moving down each configuration, we're only changing or altering one of these columns at a time. So in this first configuration, the bearing is off, the bus electronics are on, the ADCS electronics are off, the reaction wheels are off, and the cryocooler and the payload are also off. Then moving down into the next configuration, the only thing that changes between the two is the fact that I have the cryocooler and the payload on. The idea is that any changes in the PSD from configuration 1 to 2 should be contributions from the cryocooler. Right. So after we have the PSD plots, to do that, to find those frequency values, we're going to use SciPy's find peaks function to locate peaks in the PSD plots and just kind of note them with nice little black X's there. We're going to fit each of those peaks to a Lorentzian profile, record the parameters, tabulate them in a table that looks like this. So you'll see that this is the frequencies identified in the X direction, and in that would correspond to the center of the fit peak. The amplitude corresponds to the strength, the power of that frequency contributing to that signal, and the full width half max gives an indication of error or spread for that peak, and that's done in both X and Y directions. Great. And then once we have those tables for each configuration, we're going to compare them. And what we're going to do is we're going to indicate new frequencies by highlighting them in green and indicate similar frequencies by highlighting them in orange. So if you look at the tables between configuration 1 and 2, I remember the only difference between these two configurations was the addition of the cryocooler. So, in configuration 2, we see lots of new modes that pop up at 16, 60, 120, and 180. And this makes sense because the cryocooler is operating at 60 hertz. So we expect to see multiples of 60 in there. And so because those values were not present in configuration 1, they're highlighted in green in configuration 2. In the Y direction, let's take the peak at 120 hertz, for instance. In configuration 1, we do see a peak at 120 hertz, as well as one in the second configuration. Now, how we determine whether it's the cryocooler or the environment, remember that was the only thing that was changed, is we look at the amplitude, and we see that the amplitude in configuration 2 for that peak was 3 orders of magnitude larger than it was in configuration 1. So we say that that was the contribution from the cryocooler and highlighted in orange to basically identify that this was a frequency that is at the same value, but its source changed between configurations. vibrations. So in summary, we use this optical metrology system to quantify jitter by integrating the PSD plots to obtain the pointing variance values, and then note any changes in the PSD plot, and then understand system dynamics by adding or altering vibrational sources incrementally and noting any changes in the PSD plot.
Can you comment on the accuracy of the system?
Sure. So the accuracy of the system is, let's go back to, trying to find the slide with the throw distance, and so it's very accurate. Over throw distances of about a meter, we can obtain something like 0.15 arc seconds of accuracy and resolution. Here we go. And that's determined by taking the resolution of the lateral effect position sensor, which is 0.75 microns. So basically, you're able to discriminate position values in increments of 0.75 microns here. And then once you divide that by 1 meter there, you get 0.1 arc seconds of resolution. And then you can increase that by increasing the throw distance. But I'll come back to this later. That is, at least for the way that we tested it, it was slightly problematic. Dealing with the fact that the imbalance in the air bearing would cause the laser to walk off the sensor for a while. But I'll come back to that in a bit. But it's the accuracy, at least over the distances that we tested, it was 0.1 arc seconds, 0.15 arc seconds. Right. Okay. So moving on to our campaign to basically test the system on a fully integrated system. I'm going to talk about, I'll give a little bit of background, not too much about the hyperspectral thermal imager mission. This is the NASA demonstration mission to obtain high resolution spectral and spatial long wave infrared images from a 6U CubeSat. It operates in low Earth orbit and will observe volcanic sulfur dioxide emissions and obtain precision agriculture measurements. It features a cryo cooler and cube space reaction wheels, both of which contribute to jitter. And in terms of requirements, high tie's 1 sigma or RMS pointing error requirement is 2.89 arc seconds over the integration time. The integration time is 2 kilohertz or half a millisecond, and the frame rate is 139 hertz. And basically, the jitter that affects the integration time will result in the blurring of individual frames that are taken, and jitter that occurs in the regime of the frame rate affects basically the spectral sampling resolution, the spectral sampling of the instrument. So integrating this into the HSFL clean room with a test bed. On the right is that figure that I showed earlier, but just kind of overlaid onto an actual image. The laser collimator sits here, the lateral effect position sensor is here, the mirror is here, and I have the directions at which data was taken noted there. The air bearing provided by physics instruments provides a motion error of less than 7 milli-arc seconds, which we don't expect to contribute to any systematic error, being that the accuracy of our system is 0.1 arc seconds. High ties was set up on the 6U jig, and the reason why we use the support jigs is because we can't actually mount them directly to the air bearing. And so on the 6U jig, it looks something like this. High ties, this is the 6U jig, and it's sitting 6U side down. In orbit, this configuration corresponds, we're interested in how, which direction of data corresponds to basically the orientation of jitter in space. So any vibrations or any jitter in the X direction will correspond to jitter in track, and then any vibrations that happen in the Y direction corresponds to cross track jitter. And that's determined by how the satellite is moving over Earth. So so when we built up these configurations of sources that we wanted to test, this is how we sorted it. So in configuration 1, we have basically all of our active sources off and only the bus electronics on. In configuration 2, we turn on the cryo cooler and the camera to actually have an active vibrational source. In configuration 3, we turn on the air bearing and turn off the camera and crowd cooler, because remember, we only want to change kind of one active source at a time. And in between 3 and 4, we turn on the ADCS electronics. And that's not an active source of vibration, but testing or repeating, repeating tests with configurations with non-active sources helps us to identify systematic errors that might occur in our system, because we expect that the results from these two are the same, because there's no active vibrational source that happened between the two. And that's a principle that kind of generalizes well. I'll talk about that later. In configuration 5, we turn on the ADCS reaction wheels at 3000 RPM. Then in configuration 6, we turn on the Z direction reaction wheel, or we turn the X1 off, turn the Z1 on, run it at 3000 RPM. And then finally, we run both of them at 3000 RPM. So I'm going to go and break down the results just by configuration. So in configuration 1, we didn't calculate a jitter value because the air bearing is off, and so would not be representative of the true jitter that occurs. But we see lots of sources or vibration modes there, likely seismic. Well, they have, but from the clean room. And in configuration 2, we turn the crowd cooler on, and we see a host of new frequencies that occur due to the crowd cooler. Like I said, the crowd cooler is operating at 60 hertz, so you expect the fundamental harmonic at 60 hertz, and indeed in the Y direction, as well as higher orders at 180, 240, 300, so on and so forth. Again, because the air bearing is off, we don't calculate a jitter value here, because it wouldn't necessarily be meaningful, but the understanding of the frequencies and where they come from is important. In configuration 3, we turn the air bearing on and turn the active sources off. And then now we actually start to compute jitter values. And we're going to use these to compare between results as well. We pick up one peak at 120 hertz, and that's due to noise. Basically, what happens is the imbalance in the air bearing causes that laser point to drift off the sensor. And because you have in a clean room fluorescent white broadband light, which has a non-zero 635 nanometer component flickering at 120 hertz. That is the peak that you see there. In configuration 4, again, we turn the ADCS electronics off and see very similar jitter values as we expect. Again, no change in the identified frequencies, which is good because, like I said, we don't have any active sources on for this case. And so we don't expect to see any massive difference in the air bearing. Maybe a little bit of settling from the air bearing going on between the two trials, and that's something that I want to characterize later on. Now in configuration 5, we turn the X direction wheel on at 3000 RPM while leaving the crowd cooler off. We see a significant decrease in the jitter values now to below 1 arc second, 0.6 to be precise. And we also see that we still see that peak at 120 that's due to the noise. The interesting thing here is that we don't see the peak that we expect to at 50 hertz, and I'll come back to that. I'll take a question on that if anybody is interested in the interest of time. In configuration 6, we turn the Z direction reaction wheel on, and we actually see 3 new frequencies as well as a sharp decrease in jitter values. The one that's identified in the X direction is drift, low frequency drift, and the 2 that are identified in the Y direction or the across track, we see a subharmonic at about 11 hertz and a peak at 58 hertz. And this is interesting because we expect that peak to be at 50 if the reaction wheels were running at 3000. And the only way that we would be able to rectify this to see if the reaction wheels were truly spinning at a rate corresponding to 50 hertz or 58 hertz would be to grab the encoder data, which we unfortunately do not have access to for this configuration. And finally, we turn both reaction wheels on and see the effect. Not a lot of change in the actual jitter values, but we actually see the addition of 2 new frequencies, or 2 new frequencies in both directions. In the in-track dimension, we see a peak here at 210 hertz as well as 368. And in the across track, we see that same frequency at 210 hertz. And this configuration, I think, really demonstrates the benefit of testing on an integrated system, where you're able to capture these like not the non-superposition of vibrational sources and their effects. All right. So to summarize a bit of the high-tie testing, we are successful in using the metrology system to obtain PSD plots without a finite element model using commercial off-the-shelf components that we aim to do. The jitter from the reaction will remain under the 2.89 arc-second requirement. And no data, of course, one of the limitations is there's no data for the most compelling test case, which was to have the crowd cooler active while the satellite's actively pointing, because that would be, of course, the most representative case of jitter. In the imbalance in the air bearing led to some noise in the measurements, and I talked about that. The support jig alters the moment of inertia by adding mass in the y direction, and it's not, I wouldn't say it's not necessarily easy to extrapolate that, to say that mass might go as 1 over jitter or something like that, just because the dynamics and how it affects that moment of inertia matrix is, I guess, a little more complicated than that, but it's something to talk about later. And I think the biggest limitation is that we only had an ADC that sampled at a frequency of 1 kilohertz, which is, of course, due to the Nyquist theorem, basically only a reliable measurement of jitter up to 500 hertz per channel. And so we cannot, with this, at least with this ADC, we cannot directly resolve the integration time jitter at 2 kilohertz. All right, so I talked about generalizing some of this stuff to other systems. So how exactly are we going to do that? Well, let's talk about some of the components that we can use. And so in theory, any position sensing detector would do, but we wanted to use the LEPS because, like I said, it's independent of spot profile, and unlike segmented detectors or pixelated ones, you don't need to offer any kind of high order correction. The LEPS that we chose is sensitive between 320 nanometers and 1100 nanometers. So theoretically, any laser source in that operating range will work. But using a visible light source obviously has the advantage of the fact that you can actually see the alignment when you set up your system without having to just rely on, say, the instruments alone. The collimator that we used, I guess, so the LEPS informs a lot of the other components that we use, right? So the collimator, so for the collimator, that would, collimate that laser beam into a nice, from the fiber optic cable into a nice laser beam, requires a spot diameter between 0.2 millimeters and 7 millimeters. That's from the data sheet. Of course, you want a spot a lot smaller than 7 millimeters because you want to give the spot room on the detector to actually move, right? So you can attain accurate measurements. So increasing the throw distance, right, that distance between the mirror and the detector I talk about, results in a greater angular resolution, but at the same time, you also increase the beam spread from your collimator. So you could opt for maybe a collimator that collimates, a little more finely, or you could kind of deal with that walk-off issue. The ADC, for the ADC, the lateral effect and the LEPS and the K-Cube have a bandwidth of 15 kilohertz with 16-bit resolution. And so if you really wanted to make the most of these components, you're going to want to spec something that can basically measure at that speed and at that resolution. How can you scale this system, right? So the idea is that when you're in the configuration that we had, we only could measure jitter basically in 2 directions, right? In 2 degrees of freedom, right? Jitter about the x-axis and jitter about the y-axis. If you wanted to measure it in 3 degrees of freedom, you can just simply add another setup orthogonal to it to capture that other degree of freedom. And the nice thing about this is that now you've basically, I'm going to say something about correlating the movements in both directions. But you can see that with laser 1, you're not going to be able to pick up any of that roll that occurs about the z-axis. But if you have a system if you have another system set up here, now you can record that roll, and that would actually show up as y direction measurements in that system. So finally, let's talk about the methodology that we use, right? The idea is that we want to examine the system for sources of vibration, and even sources of non-vibration that we can use to basically create those permutations. And you can be as detailed or as general, but detailed is better. You can be as detailed as you want in creating these permutations. And then using the fact that differences in those PSCs, because you're only changing one configuration at a time, should be attributed to the thing that you change. And so in this table, basically it shows a full, I guess, a full list of all the possible configurations that I think you could generate for testing like a system on high tide. For example, you start with everything off, you turn the bearing on, and then in the next configuration, you turn the bus electronics on. You work down this way until you hit the reaction wheels. And then once you hit the reaction wheels, you'll spin them at different rates and see how spinning them at different rates affects the jitter between the two. And then finally, you'll repeat the same thing with both of them on, repeat it with the cryo cooler, and so on and so forth. And I think you can kind of do interesting things with this, right? Because if you start to look down here, now if you turn off the ADCLS, the electronics, and turn on the cryo cooler with the air bearing on, you basically have, I would say, you basically have measurements of jitter due to just the cryo cooler. And the interesting with that is you can kind of, if you looked down here where you see the air bearing is off and the only active source is the cryo cooler, you could look at the frequencies that the frequency tables that the two configurations create or develop, and ask yourself if they're the same. You might expect it to be the same because the only active source between those two configurations is the cryo cooler. But, of course, the air bearing will make a difference. But I think you can kind of see how you can use these to I guess, create repetitive sources or repetitive tests of sources and seeing if they actually are the same or as you expect it between trials. Right, so finally, just going to wrap up with some conclusions and thoughts about what's next. So in conclusion, we presented an optical jitter metrology setup and methodology and used it to conduct jitter analysis in the frequency domain without the use of a finite element model. We can use this to investigate disturbances in components, subsystems, and fully integrated systems, and perform optical jitter testing on high tide. In theory, this allows for faster characterization and analysis for jitter at all levels because you're not reliant on always having a very accurate finite element model. And I presented this work at the 2024 IEEE Aerospace Conference and preparing a submission to the International Journal of Metrology and Quality Engineering. So kind of to pull back a bit and to look at the big picture, right? Revisiting that slide that had a typical jitter testing campaign on it, right? You can imagine that we can use this metrology system to test component level disturbances, right? You can also use it to test your bus level and your ADCS jitter, as well as characterizing payload jitter, right? And all the while, and then after you've fully integrated everything, then you can throw this metrology system on an air bearing and conduct observatory level or end-to-end integrated testing, all without the reliance really on that finite element model. And this could be cool. Like I said, I think I was talking at the conference to someone and they were saying, like, imagine if you had like a commercial off-the-shelf drone that you wanted to attach a very small Fourier transform spectrometer to scan a field or a region affected by wildfire, for instance, right? You won't necessarily have access to a finite element model of that drone, right? Much less the drone and all the components that you use to kind of pull together a commercial off-the-shelf instrument. And so if you wanted to characterize its pointing performance or basically see which frequencies from the propellers or the structure effect might be present in that image, this might be a very good alternative. And so future work, really we want to compare these measurements with in situ measurements from high tide. And that's, I think, the biggest goal, right, for any jitter testing campaign from that testing chart, right? You do your testing on ground as well as in space, and then you inform and validate the models you made in ground with those in space measurements. High tide launched, so we really want to work on validating these results. And I think the biggest thing that's missing from this work is an analysis of the accuracy, right? How accurate is this method of measuring jitter as opposed to, say, something like a finite element model? And we could test that accuracy a number of ways, right? Like I said, comparing with a finite element model, looking at the differences between the two and trying to identify anything that's systematically different and if that will affect your difference. You can also use something like the PSF motion blurring experiment to capture your jitter actively from your imaging system and see if the movement of that point corresponds to the jitter that you pick up externally. We want to use this metrology system in the development of HiTi 2, really kind of to put it through its paces, going through component testing, through full integration. And like I said in that chart earlier, right, you can use this metrology system at all levels of testing to get results. Getting a faster ADC, right, so we could actually push that right end of those power spectral density plots up from 500 hertz to something like 1,000 or 2,000 hertz. Finally, I would just like to thank the Hawaii Space Grant Consortium, the Hawaii Spaceflight Lab, HiTi PI Rob Wright, Aidan Walk for his contributions in calibrating and really kind of setting up the system, my thesis committee, and the roast lab. And I'll be happy to take any questions.
All right. So the structure of this thesis is that we are going to take any public questions. I realize that we might be short on time, so if you have to leave, it's fine, go ahead. But we'll have some public questions and then we'll ask the public to leave and then the committee will discuss among ourselves. So any questions, even on Zoom? Hans?
Yeah, just one quick, I think you mentioned it, but I just didn't understand exactly. You said you couldn't do this one specific experiment where the cryo cooler and the ADCS was on. Can you explain again why that wasn't possible?
Yeah, basically the good thing and the bad thing about testing on a fully integrated system is that everybody else is also trying to do their testing and get it ready for checkout. So it was just the scheduling.
Okay.
But that obviously would be the most compelling case because when you're actively pointing and taking data, that's when your jitter measurements or the consequences of jitter matter the most, really. Actually imaging and taking data. So that's why that would be the most compelling case to find out really if it actually meets the requirements. But yeah, that's why we couldn't get to that.
So you briefly mentioned the two laser setup, right? Mm-hmm. That would actually be an interesting experiment if managed. So yeah, you touched upon how to like relate the X, Y, X, Z. What would you be measuring actually?
Sure. Yeah. Let me flip back to that slide. Let me find my cursor. Right. So in this, so laser 1 and LEPS 1 correspond to the measurements that kind of we did in the setup that we have here. So in this manner, you can measure rotation about the y-axis here and the x-axis here, and that would give you rotation about z-axis here just results in that laser rolling, right, which is not captured by the position sensor here. And so if you can imagine if you set up one that's orthogonal to this system, you put a mirror here. Now that is oscillating up and down in the second y direction. And so you'd have one axis that's measured by both of them simultaneously, which in this case would be the y-axis. And then the nice thing that you could do with that is you could basically correlate those two measurements because you expect that the rotation about the y-axis be the same between this sensor and that sensor. So looking at the differences between those could give you an indication of any systematic error that might be occurring. But yeah, that's how you would capture that in this configuration. And the nice thing about doing it this way is that you obtain all the measurements from the same time series. So if you imagine setting up satellite in a different configuration, you'd have to rerun the test again, set everything up, and basically it would take you twice as long to get the same amount of data.
Any information, right? Thank you. Cool.
What was the dynamic range again? I forgot.
For the LEPS?
Yeah, for your system.
For
1 meter.
Could you clarify the?
So what's like the maximum displacement in arc seconds that you can measure?
Oh, before it walks off.
Yeah,
It's something like plus minus. I'm trying to think about all those plots that just had, actually, you know what, I have one here.
so
Oh.
2,000 arc seconds. or something?
Yeah.
Okay.
So yeah, these are regions where the beam would walk off the sensor, but yeah, I'd say like about 2,000 arc seconds or so.
Gotcha.
All right, last call for questions. Going once, going twice. All right, let's give Chase another hand. All right, I'm going to ask the public to leave. Same with our Zoom participants.
Okay.
That's right.
Okay.